same numerical answers. All right, so we have this is the only force, and this is also then equal to ma, because Newton's law says the sum of the forces equals ma, but there was no a, so that was 0. And the sum of the x force is equal to ma, and we know t, and we know cosine theta, and we know m, so the only thing I don't know is a, and I can find it. So we can certainly find the acceleration, we can certainly find the normal force. Does that work? So, yeah. I just want to be sure I have nothing else. All right, anybody else? Yeah.
I have a problem with adding the scalar multiples of vectors.
Sure, let's take a look at that one. So basically, they gave you some pictures that looked, oh, in one case, there was one that looked like this, where this was A and this was B. And this came over 4. So this point right here was 4. And this one was -1, 0. Is that the one you're looking at? Or at least on the one I had.
Yeah, 4, 2, yeah.
All right, so here's the thing. These are actually just coordinates of a point, but we can treat them as vectors as long as we agree to always put the tail of the vector at the origin. The thing about a vector is, unlike other numbers, I can move a vector anywhere, and as long as I keep the same length and the same orientation, it doesn't change anything about the vector. All right, so there's perfectly general to place it right at the origin. Having said that then, what we like to do to indicate that we're using a vector and not just an ordered pair is we change the parentheses to little, I don't know what you want to call those, pointing thingies. Highly scientific term. All right. So if you do that, the little sharp bracket things, that's a way that's conventionally how we distinguish that it's not an ordered pair, it's actually a vector, and the vector is assumed to always start at the origin. All right, so are we good with that? Yeah, so like we said, this is 1, 2, 3, 4, and up 2, so I write the 4 and 2, which is actually the origin that point, but by doing that, I'm implying I actually have a vector that goes from the origin to that point. It's not just the point, it's the whole vector that goes between the origin and that point. It's just a convention. Now, there was 2 different questions, and I don't remember if this is the 1.5 or if it was the a minus 3b or a plus 3b.
The 1.5a minus 3b.
All right, so we want 1.5 times a minus 3b. All right, that's what we're looking for.
Yeah, 1.5a minus 3b.
It's just this easy. If that's my a, what's 1.5 times 4? 1.5 times 4. 0.5 times 4 is 2. 1.5 times 4 is 6. 2 times 4 is 8. 1 times 4 is 1. 1.5 times 4 is 6. You can check it on your calculator if you can't do that in your head. It's all cool. So this would be 6. What's 1.5 times 2? 3. All right. So do you understand then from 1.5 times a, going 4 and 2, I just got 1.5 times 4 is 6, 1.5 times 2 is 3. All right? And now, here's my b. I'm going to multiply it by 3. What does the first number become?
-3.
-3, right? And I have a 0. What's 3 times 0?
0.
All right. Now what you do is when you add vectors, you add the x's and you add the y's. All right. So 6 minus a minus 3, positive 9. 3 minus 0, and that's your final answer. And you can draw it anywhere on your graph. Go ahead, ask.
Sorry, where did you get 3 again?
Which 3? This one?
6 and 3.
Or, okay, I have 2, and I have 2, see, it's 1.5 times a, that means everything that's in a multiplied by 1.5. So the 2 times the 1.5 gives me the 3. Does that make sense?
Yeah.
Anybody else have questions on that? This is really an essential thing. You need to know how to add vectors. So guys, there's 2 things that I need to make really clear about vectors. Vectors have 2 forms. They have polar form and rectangular form. Listen to me carefully. In physics, vectors are always given in polar form. but they can only be added and subtracted in rectangular form, but when you get done, they need to go back to polar form. Now what they're doing here is they're giving them to you in polar form. That's almost never going to be the case. What would be the case is they'd say you have a tension of 100 newtons at an angle of 30, and now you have to take that to rectangular form. So listen to me again. If you are adding vectors, which is this whole assignment is about adding vectors, when you are adding or subtracting vectors, they must be in rectangular form. They must be in x and y form, not r and theta form. But when you get all done in an actual problem, you will take them back to polar form. So we need to know how to do that. I had a chalk. Hold on. I've set it somewhere, I want to find it again. All right, so let's take a look. I've got a vector of 200 newtons at an angle of 30 degrees. What kind of a form is that? Do you have x and y values anywhere? So what's the only other option? This is polar form. Polar gives you a magnitude and an angle. That's polar form. So that's what we've got. Now if I were going to add this to another vector, I would need to get it into rectangular form. How do I get this into rectangular form? I need to know what the coordinates of this part are. So I need an x value and I need a y value. And we should, from what we've done the last couple of days, how do I get, I'm going to call this A. How do I get A sub x? It's going to be A cosine theta. Right, and in this case, A is 200 newtons. Does that make sense to everybody? Because that's what the length of it is. When I write 200 newtons, that's the magnitude of the vector. So it's 200 newtons times cosine of 30 degrees, which your calculator will know the answer to. All right, and A sub y is equal to A sine theta, which equals 200 newtons times sine of 30. And again, you don't know that number, your calculator does. And now we have it in what kind of form? Rectangular. If you're adding, and we will do this a lot when we're doing Newton's laws, we will add up the x forces and we will add up the y forces. So we need to do this in order to be able to get just the x parts or just the y parts. The good news is if you set this up so that your acceleration is only in one direction, you don't have to take it back to polar. It'll automatically cancel out in the other direction. We'll only have to have one answer. You need to know how to sometimes, but we typically won't use it. But if I did know what a sub x and ay equal, how do I get a back again? If I started knowing the components, how do I go back to polar? It's called the Pythagorean theorem. All right. If I know the sides, how do I find the hypotenuse? A squared equals ax squared plus ay squared. All right, just the Pythagorean theorem. Now, that gives me the length, but I need the angle. How can I find this angle if I didn't know it was 30? If this was just theta, how could I find this if I knew this was ax and I knew this was ay? What trig function involves the opposite of the adjacent? SOHCAHTOA, right? Tangent. Good. So what that tells me is that tangent theta is equal to opposite over adjacent. So this is how I get the rectangular coordinates, and this is how I get the polar coordinates. And by the way, I kid you not, all your calculators know this. They have a special button that will do it for you. All you have to do is push it or enter the numbers in particular order. I highly, highly recommend that you figure out how to do it on your calculator because it will save you a lot of time on tests when we need to find these things. If you don't want to bother, it's your right and you can always do it this way. There's a slight problem in getting the wrong angle of doing this. And that's because tangent is positive in 2 quadrants and negative in 2 quadrants. So you're not sure which quadrant it's actually landing in if you do this way. Your calculator will never make that mistake because they're all programmed to recognize which quadrant it goes in and gives you the right answer. If you don't have the manual for your calculator, I know this will shock you as part of the new generation. Guess what you can do? You can go online. All the manuals are online. They'll tell you exactly what keystrokes to put into your calculator to do this. If you don't have a calculator that does this, I highly recommend this really expensive calculator. It's the Casio FX300 and it cost me $9. All right. I understand sometimes you can get it on Amazon for $7. Okay. Yeah. I told you the story. My first calculator was $450, and it didn't do half of this. So times change. It's a good thing. All right. So any other questions on this? Basic. All right. Then and we're done with any questions. I hope that the reason there's not questions on the homework is that no one has done it except for a few. Guys, if you don't get on the homework as soon as you can, it does, like right now, you're not going to see me again until Wednesday of next week, and the test is, and we have a review session after Wednesday on Friday. The test is Monday. So, the sooner you can ask questions, that would be a really good plan. Okay. If there aren't any other questions, I'm going to move on to some other stuff. Okay. I'll take that as, yeah, let's do some other stuff. Couple basic questions. How many objects does a force require? 2. And Newton's third law basically says that if you've got 2 objects creating a force, what can you say about what I describe what's going on? 2 objects. So I have, okay, you and the football. I kick the football, there's a force. But how many forces are actually present when I kick the football? 2. My foot on the ball on my foot. Which one's bigger? They have to be the same, right? They have to be the same. The forces are always exactly the same but opposite. So why does the ball go flying away? Because Newton says the sum of the forces is of the external forces is equal to ma. All right. So if the force on me and the force on the ball is exactly the same, what's different on this side that tells us why one of them does all the accelerating? The mass of the football is so small, especially compared to my mass, that it does all the accelerating. Now, even more than that, guess what? It's not exactly just because I have more mass. It's because there's such a thing as friction. So when I kick the ball, friction ties me to the earth. So actually, it's the mass of me and the entire earth versus the football. So the football really loses in every which way. Okay? So that's an important thing. When I draw a free body diagram, I never draw forces that don't act on the thing I'm drawing. So even though that object exerts forces on other things, like I push my hands on the desk, is it my hands pushing on the desk that lifts me up? No, what lifts me up? Just pushing back on me. Because if this was water, I'm never going to go up even though my arms are just as strong as they were before. The thing that lifts me is if it pushes back. All right, so I push and it pushes back, and I go up. It has nothing to do with the strength of my, well, a little, I mean. But the thing is, it's a combination. However hard I push on it, it pushes back with the same thing. That's what's going to lift me. Are you there? So we're only interested in the forces that act on the object. And that's what the whole beauty of a free body diagram is for. So we're going to do a few examples here. And I'm going to hopefully tie them all together. So these should look familiar. We've done them in labs, but I'm going to do them quite formal. So I have a frictionless table, a pulley, a mass M1 tied to a mass M2 that's over a pulley, and I want to find the acceleration of the system. All right, so let me just specify M1 is larger than M2. Since M1 is larger, is it possible for M1 to be so large that M2 can't move it? Yes, because you're used to everyday life, but did you hear what I said at the beginning? We're going to say this is totally frictionless. And if it's frictionless, is it possible for M1 to be so large that M2 can't move it? And the answer is no. As long as the surface is frictionless, even if it's a tiny force and you have to wait a week, it will eventually pull. All right. So here's the thing. How do I set this problem up? How many free body diagrams do I want to draw? Two, because I have two masses. It turns out, guys, there is a way to look at this outside the system, and I'll show you that as well. It's actually faster, but the problem is it's not as powerful. So it fails rapidly, but on a problem this simple it works. But we'll look at the other way first. So I have two bodies, and I pull them out, and I draw them as separate. And here's the thing then. M1. What are the forces that act on M1? I have tension, and I draw from the center. I draw from the center out. All right, so tension. I have weight, M1G, and normal force. All right. And anything else? Okay, now let's look at M2. What are the forces? This is hanging in the middle of the air. So I have no normal force because it's not weight. And I think somebody said it, I just didn't hear them clearly. Tension. All right, so we have tension up here. So we have tension up and the weight down. Okay, now in these two problems, do they share anything? The tension's the thing that's common between them. All right, so what's the next step that I do? I've drawn my free body diagram. Now what decision do I need to make? Can I just start adding forces? You sensed a trap in that question, didn't you? Everybody got quiet. Yeah, there was a trap in that question. I can't add forces because I haven't defined a coordinate system. Without a coordinate system, I have nothing to add. Because if I chose this one, not only would you hate me, I would hate me. All right? Because it's a perfectly valid choice, but it makes the life really tough. If this thing accelerates at all, what direction does it accelerate? To the right. And so our choice must always be that one axis lies along the direction of acceleration. So we choose a coordinate system that looks like this. All right? So that's what governs my coordinate system choice. All right, with that choice, I now sum up all the x forces, and what do you get? Just the tension, right? There's nothing else. Tension's the whole thing. So the sum of the external forces for this block is tension, and by Newton's second law, what does the sum of forces equal? MA, right? All right, so this just equals MA. And I'm going to say M1A because that's the thing I've got going. All right, so I have that. What's the sum of my Y forces? All right, so I have N minus M1G, and somebody said, and the answer is 0 because if the acceleration is all in that direction, then it has no acceleration here. Do you understand where I'm getting these numbers? N is up, that makes it positive. M1G is down, that makes it negative. All right? When we're in one dimension, plus and minus is how we indicate direction. So things that are down, we make negative. Things that are up, we make positive. So on this one, this is to the right. So for x, that's positive. If it had been to the left, I would have made it negative. And we're ready to roll at this point. Now, in terms of acceleration, this is true but not useful yet. If I were dealing with friction, this would be necessary because the friction is tied to the normal force. All right. And hopefully I'll get there, but if I don't, we'll do that next time. All right, so that's where we go with this one. Help me write through here. Do I need to worry about summing x? No, there are no x forces, so I immediately go to the sum of the y forces. And what are they? T minus M2G. How did I know to write it that way? Because T was up, therefore positive. M2G is down, therefore negative. And this should equal what? By Newton's second law, it should equal M2A, right? Am I done? I'm going to hint, we're not done. I've left something very crucial out of this which will mess me up. And I did it accidentally during your lab, so we will not be doing that again. It's negative because if we look at this picture, what's the only way this is going to move?
We go
Down. So MA has to be down, therefore has to be negative. Negative is used to indicate down. Is MA a force? See, this is where math and physics are different. This is a force and this is a force, and I say it equals. So it seems like it ought to be a force, but it isn't. This is cause and effect. So mathematically they're equal, but this is not a force, it's the result of forces. Never in a free body diagram put MA anywhere. Forces have to be caused by two different objects, and if you can't think of the two objects involved, you're probably mixed up. What's the object other than M2 that's involved with T? M1. All right, they're tied by a string, they pull on each other. What's the body other than M2 that gives me M2G? It's M2 and the big thing we stand on, Earth. Guys, it's really critical. You've got to get filed in your brain. If you're ever doing weight, Earth is the other object, unless you're on the moon. All right, whatever planet you're standing on is the other object. All right, so we've got that set up. Now, what we can do is we can say, I know that T equals M1A, and so I can just make a pure substitution right away up here. I can say M1A minus M2G equals minus M2A. Anybody have any questions what I just did? I took this equation, but I realized from here that T is equal to M1A. Okay? What am I looking for? What's the only thing in here that we assume is not known? A. M1, M2 are assumed given, all right? Because that's the whole problem. I said, I've got M1 on the thing, I've got M2 there. Anything that we give that's labeled is assumed to be a known quantity. The thing that wasn't labeled and that we're looking for then is A, because G is a constant that is well known. So in order to do that, I get everything with A on one side and everything else the other side. So I get M1A, I bring the negative M2A to this side and make it positive, M2A, and I bring the negative M2G to this side and make it positive. Everybody see what I just did? I did two algebra steps at once. I will go over them as slowly as I need to, but I'm going to push you.
Don't we have all the terms like A by itself?
Yeah, so I got all the terms of A on one side, and I got everything else on the other side, and I'll do my factoring and get A by itself. But the first step in solving for an unknown is get all the terms with that unknown on the same side, and then factor it out, if possible. All right, so I get A times M1 plus M2 equals M2G, or A is equal to M2 all over M1 plus M2 all times G. Here is a guide which for a long time will be correct for any problems we do. If you're solving for A, you better see the sum of all the masses in the system in the denominator of your answer. If you see any minus signs in here, you're wrong. There can only, this should end up being a sum of all the masses involved in the problem in your final answer here. I mean, there can be times where maybe one thing equals the sum of two others, but what you can't ever have here is a minus sign. It's got to be the sum. And now here's the other way to do it, which is much simpler, but only works in special cases. If instead of taking M1 and M2 as separate things, what if I take the entire system, M1 and M2? You got the idea? Tension is now an internal force, isn't it? So it's not acting. So in terms of the forces that act, that don't include tension, that are outside the system, I have a weight for M1, I have a weight for M2, and I have a normal force on M1. Those are the external forces. Does that make sense to you? Is it true that the M1G and normal force cancel? If they didn't cancel, what would M1 be doing? It would go, it would accelerate up or down, and that's not happening. So they clearly cancel. What of all the external forces acting, what's the only one that survives? This weight. Right? Look, here's the external forces. M2G, M1G, and normal force. All right? These cancel because they're equal and opposite. This is the only thing that survives. The equation says the sum of all the external forces is equal to the acceleration over the total mass. All right, so since that's the only thing, and I'm good. All right. So what that tells me then is that negative m1g is equal to negative a over m1 plus m2. The negative because I know that it accelerates down from the picture. So the negatives go away, and I get, excuse me, I did that entirely upside down. That's supposed to be an m2. So did I do that right?
Why is it over M2?
It's not over, it's times. Did I do that wrong over here? No, I didn't. All right. Sorry. But when I talk, sometimes I'm doing stupid things. So this is the external forces equals to m total times a. Sorry. So m1 plus m2 times a, and a is negative. And that just takes me to this equation here. So you can do it just by looking at the whole problem at once, but it gets harder and harder to see your way around. This is a little longer, but it's much easier not to make a mistake doing this method. All right, but we did get exactly the same answer. All right, so I'm going to say that we got A is equal to M2 over M1 plus M2G. Okay, and now what we're going to do, you all have your notes from last time? So rather than read or write this, it's in your notes, and because we have short time, I want to just put the answer up. Okay, so what I have, the output machine, I've got two different masses. I need to specify one of the others, so I'm going to specify that M1 is larger than M2. All right, and so what we ended up getting there is that A was equal to M1 minus M2 all over M1 plus M2 times G. And that should be in your notes from last time. Now, we're going to do the wickedest one. All right, so on this one, what we have, and we're going to keep frictionless, all right? We're going to stay frictionless. I have a pulley, I have a mass, M1, and another mass, M2. And I want to find the acceleration of this system if the angle of that slope is theta. Okay, which way does this move? Work with me for a bit. If that angle got so big that we had this situation, which way would it move? This would go down and this would go to the right, right? This would be going this way if this angle were big enough for this to happen. On the other hand, if it was an active machine, and I bring this all the way down and this is a bigger mass than that, now which way does it move? It's going to go this way, right? How do I know which way this is going to move? Because I just showed you it can move two different directions on the extremes. So the answer is I have no idea which way it's going to move. And the cool thing is, it doesn't matter. I pick a direction, and I solve it based on that choice. If my final answer is positive, I picked right. If my final answer is negative, I picked wrong, but I don't have to solve it again and just say, oh, the direction is the opposite of what I said, and the number stays the same. So don't sit and try to figure it out. Just choose. We do that a lot. We'll just choose a direction, and then we'll solve the whole problem based on that. So with that in mind, I have this and this as my three body diagrams. I'm going to let you choose. Which way do you want us to go, up or down the plane? Up. Okay, having chosen that, we have to be consistent. So here's the thing. If this goes up the plane, which way does this go? Down. So this will have a negative acceleration. if it were going to go down the plane, this would go, and we'd have a positive acceleration. So be sure that once you pick something, make the other one do the logical thing. If this is going to go up, this has to go down. If this is going to go down, this has to go up. All right. Now, with that in mind, let's do this one first because it's going to look really familiar. I have M2G and I have tension. Anybody got any problems with that one? Right? It's just the same thing as we've already done. It's a hanging mass, it's got a weight and tension, end of story. This one's trickier. Let's first put the forces in and then we'll make another choice. So what are the only forces acting on this? Weight. Alright, so we have M1G. There is a normal force, but remember, what's the definition of a normal force? It's perpendicular to the surface. So if that's my surface, my N has to be this direction. Does everybody see that? Okay, what other force do I have? Tension. And tension, I was telling somebody else today, my grandmother used to have a saying, you can't push with a rope. And what do you think was the meaning of that saying?
What was the saying?
You can only pull with a rope. So she's saying you can't do impossible things. So if you're trying to do something, she would say you can't push with a rope. In other words, if you're trying something that can't happen, you can only pull with a rope. All right. So in this sense, this is a rope. You can't push with it, so it's got to pull. All right. So my tension is like this. Everybody with me? What are those things I just spent time drawing? Free body diagrams. They will be on the test. All right. Absolutely. No two ways about it. These will be on the test somewhere. Meaning draw free body diagrams. Now, after I got my free body diagrams, the next step, coordinate system. And how do I choose it?
Whichever axis has acceleration.
Excellent. So let's start here. If it's going to accelerate, it's going to have to be vertical, right? So that gets this one solved for me fairly easily. This one is pretty easy again, but because it's going to accelerate along the tension, isn't it? And so, right, so this is my coordinate system. I'm dotting it because there's too many other lines going on in there. All right. Now, if I say that this angle is theta, where does theta show up in this picture? Let's kind of, so I say I've got this, and I've got that, and I've drawn my coordinate system like this.
Theta is negative? It's not supposed to be negative.
No, we're always going to choose theta less than 90.
Okay.
In other words, we always, when it's bigger than 90, we choose the other side to be theta or whatever. I guess that's not always true. It's always less than 180. But so if this is theta, I mean, my choices are, look here, I've got this angle, I've got this angle, certainly not any of those. So it's either this one or this one is theta. You can either memorize this or understand it. It's always between the axis and this. And the reason for that is that if you take a look at this, what happens, this angle, let's call this angle alpha, all right? This angle and alpha and 90 degrees, right? So we've got this, we're going to say this is, we don't know what this is, all right? But now look at this. This is theta, this is 90 degrees, and this is alpha. So alpha is exactly the same, isn't it? We have theta, 90 alpha, that's got to be theta to make it, because all triangles have to add up to 180. So the only way is if this is 90 and alpha,